Okay, yeah, I'm very happy to be back here at JarCon. So we as the manufacturers of USRPs have been sponsoring this conference since the first conference. So I'm very proud that we have this continued tradition and we're back here. So this slide says Ettus Research/NI and it also says Emerson. So I quickly want to talk about that because I've gotten so many questions on, so what's the state of your company? What do you, how do you operate these days? And is SDR still a thing? And the question is, justified because if you have, been following anything about NI, so there was 5 years ago, we had the blue logo NI and we had the green logo Ettus Research, and then a million things happened and company got sold to Emerson, so we have another new blue logo, and it was new leadership, and everything got reevaluated. And so as a consequence, many of you guys have approached me directly at this conference and have asked, so what's the state of SDR at NI? Is it still a thing? Are we going to keep doing that? And the answer is yes. So it was, scrutinized, of course, and it turns out SDR is still a great product, and it makes total sense to keep doing that. And in fact, we're going to be doing even more of that. So there's been an increased reinvestment in the SDR product line. We're putting more people on it. And also just the concept of having this open source based SDR itself was considered sensible and worth continuing. So we're back. There's plenty of people here at the back. Maybe you can raise your hands real quick. Yeah, so if you have questions about products, you can approach any one of those or myself. But yeah, that's enough going on about our company. I want to talk about stuff that we've been doing. I don't have a new product, hardware product, to present this year, but we already have a lot of really cool hardware products. So I'm going to quickly go through them one more time, because I think one thing that we do really well with our SDR, the USRP product line, is sort of cover this huge space of possible applications that you might care about. So at the top left on this slide, we have the low swap devices, USB-based, smaller channel width, but also really easy to set up. The bottom right, we have the USRP X440, which can capture 1600 megahertz of analog bandwidth instantaneously with 2000 megasamples. And in between, we have everything else. So the USRP X310, still a really good device, RFNoC capable, can do Ethernet, has different daughter boards, so it can cover different frequency ranges. The top right, we have the deployable devices. They're either small, like the E310, or ruggedized, so you can deploy them in all sorts of environments. And then at the bottom, of course, are high-end devices. They all come with an embedded processor, so they run Linux natively, and give you different frequency ranges up to 8 gigahertz. Directly, you can use additional up and down converters and really high bandwidths. And on the software side, we also provide all sorts of options. So I guess most of you would be using the open source workflow with the USRP, so using our UHD driver, and then using the C++, or Python APIs to call into UHD. That's what most people do. It's also really powerful. But you can use GNU Radio, of course, so that's still front and center for us. We make sure that GNU Radio support is always a given with any USRP that we release, really on day one. But if you don't mind going into proprietary software, we have that as well. So we have support for MATLAB and LabVIEW, of course. The only case where you really do need to, buy some piece of software is if you want to do FPGA development, because we do have our RFNoC framework, which allows you to deploy all sorts of IP onto the FPGAs of the USRPs, making them even more sort of useful in different environments. And that's where you're going to have to get Vivado. But other than that, really, the choice is yours, and whatever workflow is most relevant to your kind of work, that's what you should be choosing. Now, if there's anything that you think you should be able to do with an SDR, but you can't, I challenge you to go to either Marcus or Ben Coffin, the guy who looks like he plays in a heavy metal band, and Marcus, the tall guy on the left. See if you can challenge them, poke them questions like, why can't I do X? Because I think we have a pretty good array of devices available. All right. Now there's really two things I want to actually go on into in this talk. And I'm going to start with things that are happening outside of the USRP product development team. So of course, like NI is a big company, and I'm on the team that develops UHD and builds USERPs, but there are also plenty of other teams doing research or other kinds of work. And I do want to talk about that because there's some really interesting things coming out of those teams. So first of all, we really like enabling researchers to do their, to solve their RF-based research problems. So in particular, if you are into 5G, 6G, future G type of research, then one of the products that we have available for you is like a bundle of USRP and OAI. So OAI is a open source 5G software stack. It provides GNodeB and UA implementations, and it's modifiable, so you can look at the source code and instrument it at all, various layers, and that's really, really key and important if you're a researcher and you want to poke around in the 5G stack and see what's going on, maybe make some changes, see if you can improve something, or see if you can break something, right? Why not? You can do some security research at this point. And we've officially bundled OAI with USRPs because you always need some kind of hardware to make it go over the air, and become a member of the OAI Alliance, and we try and make an effort to make it easy to integrate those. So it's a really good starting point if you're into 5G, 6G research. And we've actually made use of that ourselves, which I'll get into in a bit. But if you're not so much in the telecommunications research, maybe you're doing EW or radar work, we also have something for you. So I've linked a white paper here. At the bottom right, you can see a screenshot of Hayden Nelson, who's usually at this conference. It's the first year he couldn't make it in a long time. Showing off the USRP X440 wideband capabilities. So like I said earlier, you have 16 megahertz of analog bandwidth that you can play around with. So what can you do with that? And that's what we talk about in this white paper. And it's definitely, it's definitely a solution that we'd like to provide. Okay. A huge hype that you've all been in touch with somehow, at least you must have heard of it, anything that's AI, ML related. And now NI is a test and measurement company. So a big question that we've been mulling around in our heads is, how can we get involved in test and measurement when NI, ML systems are involved? So imagine you're a manufacturer of telecommunication devices that use machine learning. Like maybe this leads to unintended consequences of how the device works. Maybe you want to be really certain that despite there being these neural networks inside your device, they work in the way you've intended. How can you verify that that's true? Like what kind of validation do you have? And that's something we've been thinking about. And some of our colleagues have been working on that specific question in the domain of wireless systems. Now there was a cool little sort of side project that came out of that, which is the RF data recording API. This is something that came out of a collaboration with Northeastern University. It's a set of utilities that you can use if you need to create large data sets for training AI models. So you have a bunch of USRPs and you want to sort of capture or generate signals. This RF data recording API is a tool that allows you to capture a whole bunch of RF signals, store them as SIGMF data sets, and then use them as inputs to your AI training model. So you can use this for all sorts of applications. But the main work that this team did was thinking about how to test DUTs that are themselves ML-based. So here's an example of what we call a neural receiver. Neural receiver is really just a fancy word for saying we're going to take a modem, in this case 5G uplink, replace the existing classical receiver with its MMSE equalizer and whatever with a neural-based receiver. So the specific implementation is called DeepRx. It's not something that we created ourselves, that we integrated it and started to do some analysis and capture some data. On the right-hand side, you can see some BER curves and see how the neural receiver behaves differently compared to the classical receiver. That's the kind of result that you would get out of such a setup, so really useful. But how did they do that? And this is the setup, and I think it's a really cool setup. I just really love this slide because it has like so many components in there. that are all really interesting by themselves, and then you put them all together to create this really cool product. So in the middle, bottom middle, there is a real-time channel emulator. It's based on PXI hardware from NI, and it can be used to generate RF channels. So when you're doing your test and measurement setup, then you don't have to rely on over-the-air transmission or anything like that. You can actually control the RF environment by having this channel emulator. And then we have a UE and a G-Node B based on the combination of OAI, Open Air Interface, and USRPs. Put it all together, you have this end-to-end uplink that you can fully control. And on top of that is orchestration software that we also created. So, and this is the kind of test and measurement setup that you could use for testing ML-based DUTs. So in this case, what it did was, first of all, switch out the classical receiver between with the ML-based one, the DeepRX-based one, so you can go back and forth between those. Also, modify the channel emulator to generate different environments, so you can actually have more realistic results. And then, play back the whole thing. So start an uplink signal, start a data transmission, and then on the other side, figure out what your data error rates were, like your block error rates or bit error rates, or whatever your metric is, and then see how they behave over time, over frequency, over varying channels, and so on. Yeah, so this is a really, really nifty, real-time capable testing setup of ML-based DUTs using everything that we have to offer. Like we have UHD, USRPs, OAI, and of course NI-based testing software on top of that. Yeah, this is a really nice project. There's also been papers and other conference articles published on that, so I can provide links to those. But for the rest of the time that I have, I actually want to go into things that we did build around USRPs and UHD in the last year. So, new features. Like I said, we didn't have any hardware, but that doesn't mean we've been sitting on our hands for the last year. We've been pretty busy improving UHD and also RFNoC. Quick raise of hands, is anyone familiar with RFNoC? Does that ring a bell? Have you heard of that? I see about half the hands, so that's great. That's really good coverage. So RFNoC, I don't have an intro slide on that, is the architecture or the framework that we use to deploy IP on the FPGAs of our USRPs. So if you buy a USRP just off the shelf, turn it on, what you can do is you can receive and transmit data. You can pick the center frequency, you can pick the data rate, gain and stuff like that. With RFNoC, you can also modify the data signal processing, like the data paths. So you can, if you need an FFT or an FIR filter or anything else like that, you can put that on the FPGA yourself. Now, in most cases, if it's custom signal processing and not something very standard, you might have to do some development by yourself on the FPGA, but we provide all sorts of tooling for that, which I'm going to talk about in a sec. But if you are just using standard DSP components like FFTs and filters, or other things that we might provide, then you don't have to do any FPGA development. You basically run a tool that says, hey, I would like to reconfigure my USRP to have an FFT in the data path, and push a button, and that's what we've been working towards. Okay, since last GRCon, we've had 2 UHD releases, and as you know, since we do open source development, every feature that we finish gets pushed public onto Git until the next release, so you can get a sneak preview of what's coming by following, our Git branches. I'm going to highlight most of these bullets on the following slides. A couple of really small things, but things that I personally find really useful. I'm just going to talk about right now. So, for example, really, really small thing, but I just love it. It's just better release notes. So the last couple of UHD releases, I don't want to say I'm too proud of those, but if you go to GitHub right now, you look at the latest UHD release, 4.7, you get a really nice description of what's going on. It's much easier to understand of what we changed, in some cases even why we changed it. And something else we've been asked a lot about, but I'm not going to talk about in the following slides, it's just finally updating the embedded Linux on our USRPs. So now they all run Kirkstone. I don't know the version number, we just use the code names. So, but that's a more recent version, and also, we have plans for keeping that up to date. All right, so I'm going to pick out a couple of these features and for the rest of the remaining time that I have and go into some details. So first of all is the dual rate feature, which we released with UHD 4.6. So that was actually not too long after last GRCon. So last GRCon, we introduced the USRP X440. I mentioned earlier the device with the huge bandwidth. One common request that we had was the ability to capture the L band in one go. So if you can digitize at 1600 megahertz of instantaneous analog bandwidth, that shouldn't be too hard, right? Because the L band goes from 1 to 2 gigahertz, so we have 1 gigahertz of bandwidth that we need to capture. Should be easy, except the USRP X440 has a pretty raw interface at the front. It has no mixers. You have to bring your own up and down conversion in many cases. It has many channels, but it does not have any filtering or analog front end like the other USRPs do. So capturing the L band is actually not as simple as it sounds, because what rate do you set your analog to digital converter to? The maximum rate that this device can do is around 4,000 megahertz. But if you set it to 4,000 megahertz, you get a Nyquist gap right at 2 gigahertz, and that sort of limits the visibility into your L band that you can capture. I gave a full talk about all of that last year. But what's the answer? Because you can't, you can't tune in an analog sense. And if you reduce the converter rate, then it gets even worse, because your Nyquist zone boundary will be moving right through your L band. And the hardware had the capability, and now the software does too, of using different sampling rates within the same USRP. It's something we haven't been able to do in previous devices. So in this case, you can run one channel at 1024 megasamples and the other one at 1280 megasamples. Gives you a different viewpoint onto the L band. Stitch that together, and there you go. That's your L band coverage right there. And of course, that feature can be used for different applications than just covering the whole L band. Like you could have a receiver at telecom rates running on one channel, but then a different rate receiver on the other channel. That's another option that you can do. And we've had to do all sorts of changes to the underlying framework. RFNoC was previously unhappy about supporting multiple clock rates. Now it's fine. And that was sort of the main feature that came with UHD 4.6. And then with the recently released UHD 4.7, we've been making it much more accessible to use the FPGA capabilities of the USRP by making the RFNoC tooling just much more easy to use, less error prone, and more helpful. So we have a tool called RFNoC Image Builder. Who's used RFNoC Image Builder in the past? Not a few, like 1, 2, I see 3 hands. And you know what? I don't blame you. Like, the tool was not great. We've used it internally, but we also wrote it, so whenever it threw a random bug, we kind of knew what it meant, but we hadn't really sort of focused on the usability aspect of that tool. And that's something that's changing now. So with UHD 4.7, we've completely redone that. So a big problem that you might have is you could build configurations that were not actually that useful. So to sort of give you like the background, this image builder needs an input file where you describe what you want it to have. So I mentioned earlier you might want to have an FFT or an FIR filter. That's exactly what that file says. So you say something like, I need 2 channels, radios, I need resamplers, and I want an FFT on this channel and an FIR filter on that channel. Please go build that. And if you were lucky, it built you the right bit file. If you were unlucky, it built you a bit file, but that didn't work. If you were somewhere in the middle, it gave you an error message, but it might not be super helpful. And we've changed that by making error messages much better. Not only are they more useful error messages, they also give you an answer, like a solution. It says, hey, this doesn't make sense, but maybe try doing this. So I think you were trying to achieve that, but looks like you didn't do it correctly. What about this? One thing that we did to achieve that is to add all sorts of checks. I don't know if you can actually read that from back. I can't read this from here. So, but like the configuration files that describe the individual components can now be amended by checks. And these are really simple lines where it says, I want the number of channels to be less than 4 or something like that. And so basically at the very first glance at the configuration files, our tool can tell immediately if the configuration makes any sense. And this is also a feature that is available to anyone who wants to write their own blocks and put them into RFNoC. GNU Radio integration is getting better and better. So something that will be coming back in the future, and this is a preview, this is not completely done yet, is the ability to build bit files for FPGAs out of the GNU Radio companion. So you have a graphical overview, and that is really nifty because I mean, I like writing sort of text-based descriptions. I don't mind doing that, but they're not intuitive. They don't provide you like the right sort of haptical intuition of what's going on the FPGA, because you like in the text file you say, oh, I want an FFT, you write that at the top, and then further down you say, oh, by the way, I need to connect the FFT with, I don't know, this other block. In the graphical representation, you can immediately see what's connected to what. So I kind of like that. And something that we've been asked about for many, many times is RFNoC mod tool. Oh, I thought it was on that slide. Okay, that's fine. I have more on RFNoC mod tool later. So I mentioned earlier, with RFNoC, you can choose what's going on the FPGA. So you can say, I want an FFT, I want an FIR, and I want my radios, and I want to connect them in this way. However, that wasn't all the features that the USRP has to offer. So we've expanded the capabilities of RFNoC towards people building their custom bit files as well. And one thing that we've added is the capability, at least for the X400 series devices, to also choose the transports that are available. So the transport is what puts data in and out of a device. So in case of the USRP X440, that would be either 10 gigabit or 100 gigabit Ethernet. So within the same configuration file where you choose the blocks that you want to have, you can now also choose which kind of transports you want to have. And you can connect pins in more configurations. So you could say, well, I'm not going to have any 100 gigabit Ethernet at all. I'm going to take these pins that are connected to the SFP at the front, pull them straight into my own block where I'm going to implement an Aurora protocol or something like that. So it gives you much more options. One thing that we've also added is make it easier to put in proprietary IP. So so everything in UHD is open source, and it's going to stay that way. That's not going to change. But we've gotten requests for people to drop in closed source IP as well. And just to make that mesh more easily, we've also improved the infrastructure around that. Okay, so if you want to simply take existing blocks that we provide, and they include FTs, FIR filters, then simple math, splitters, combiners, those kind of blocks, you're fine. Like really, that's all you need. But you might also want to write your own RFNoC blocks and then include them in the design. That's also something that we've supported for a long time, but we also made that a lot easier now. So in the GNU Radio world, you're probably familiar with the concept of out-of-tree modules. So you want to have GNU Radio processing blocks that are not part of GNU Radio, but you still want to include them in your GRC flow graph and whatever. The same concept applies with RFNoC. So you can have your own RFNoC blocks. And if you want to do that, you're going to have to write Verilog or VHDL or something. So this is not for the faint of heart, but it's something that we've also made a lot easier. So in UHD, we used to have an example for an out-of-tree module called RFNoC-example. And we've completely cleaned that up, redid that. It's now called RFNoC-gain because it has a gain block in there. And it comes with a whole bunch of new features, including GNU Radio examples. So, you just much better README file, explains what's going on, like what you put into which individual directory and how to use this. The GNU Radio examples come in different flavors, and they're also just like part of the package. So this is also something we've just gotten a lot of questions, like, oh, how do I integrate RFNoC applications in GNU Radio? It's right there now. There's no more mysteries, or people have been sort of sharing secret tips on the mailing list. Like, that's nice, but really that's not what we want. We want it to be immediately accessible to everyone. And of course, RFNoC mod tool is the utility that you use to generate the boilerplate if you want to create your own blocks, like a modem or whatever it is that you want to integrate on the FPGA. It's also come back with a 4.7 UHD release, and we'll continue to get more improvements. Just a small thing, but like a lot of people have asked about this, and I think it'll it's one of those tiny things that will make some people's lives a lot easier. Like we've always had an FFT block. In fact, it was probably the first RFNoC block we ever wrote, and it really didn't get a lot of attention. But we've been redoing that, so this will be released soon. Increased size limit for FFTs. Now I know people have asked about million-point FFTs. We can't do those yet, but we can max out the available size of the Xilinx FFT IP core that we're using under the hood. So that's 64K is now the new size limit for FFTs. But more usefully, we can insert and remove cyclic prefixes now automatically within the same block. So you want to build a OFDM-based modem, do some pre-processing on the FPGA, boom, there you are. It's right there, part of UHD. Okay, that's the last feature I had. So I just wanted to encourage everyone to come by the booth. It's where all the other booths are. Talk to everyone wearing an eye gear. Right now they're standing at the back of the hall, but usually they're standing by the booth. Also, we have an RFNoC workshop led by Neil Pandya, whom most of you know. I think it's tomorrow. Yes, it's definitely tomorrow. Come on to us, talk to us, and like I said, if you have any challenges, something that we should be able to solve with USRPs, and you think we can, talk to us as well. All right, thank you very much, and I'm really glad to see you all again here at GRCon.